Hi everyone. Today's video is about divisibility in polynomial rings. We ended section 4.1 with a discussion of the division algorithm for polynomials over a field. That discussion should have reminded us of the division algorithm for the integers. Today in section 4.2, we'll be seeing notions such as divisibility and greatest common divisor applied to polynomials that should again remind us of the situation for integers. Now we'll let f here and forevermore denote a field, and we'll start with two polynomials, f and g, in capital F adjoin x. If g is not the zero polynomial, we say that g divides f exactly when f is a multiple of g in capital F adjoin x. That is, if f of x is equal to g of x times h of x for some h of x in F adjoin x. A polynomial is monic if its leading coefficient is 1. And if f and g are not both 0, then the greatest common divisor of f and g is a monic polynomial d of highest degree that divides both f and g in the polynomial ring f adjoin x. That was all rather quick, so why don't we do an example? We'll consider polynomial f of x, the fifth degree polynomial that you see there, and g of x, a fourth degree polynomial. Both of these polynomials are polynomials with rational coefficients. Now, if you were to try to divide g into f using the division algorithm, you would find that you would get a non-zero remainder. So g does not divide f. However, the polynomial 6x squared plus 17x plus 12 does divide evenly into g of x in this polynomial ring, because we can write g as 6x squared plus 17x plus 12 times x squared minus 4. It's also true that this same polynomial, 6x squared plus 17x plus 12, divides evenly into f of x. Now, we know that 6x squared plus 17x plus 12 cannot be a greatest common divisor for f and g because the polynomial fails to be monic, right? The leading coefficient is a 6, not a 1. However, if we divide through by 6, we wind up with another polynomial, x squared plus 17/6 x plus 2, that lives within the polynomials with rational coefficients. It does, again, divide both f and g, and it turns out that it is a greatest common divisor for f and g, meaning that it's monic, first of all, right? The leading coefficient is 1 there, and there's no polynomial in Q adjoin x of higher degree that divides evenly into both f and g. One thing we should know about divisibility in polynomial rings is that the basic ideas or theorems about divisibility in the integers also hold for polynomial rings. For instance, suppose I have a polynomial that divides evenly into f and evenly into g, then that polynomial will divide evenly into the sum f plus g and into the difference f minus g, etc., etc. These results hopefully will remind you of similar results that hold true for the integers. Now, I just came out and told you that this polynomial x squared plus 17/6 x plus 2 is a greatest common divisor in Q adjoin x for these two polynomials f and g. How in the world would we determine that? it seems that it's not obvious at first sight that that should be a greatest common divisor. And it seems that these computations with polynomials are going to be a bit harder than they were for integers. Before we make more computations with divisibility, it's probably good to have a few facts under our belt regarding greatest common divisors. Here we have this important theorem, 4.8, which says that if we start with two polynomials, f and g, inside our polynomial ring, and if they're not both 0, then there is a unique GCD, d, for f and g. And further, there are polynomials u and v, with u times f plus v times g equaling d. Now, if that theorem rings familiar, it should, because there's a theorem in Chapter 1, I believe it was Theorem 1.2, for the integers that looked very similar to this, and might be a good idea to go back in your book and have a look at that theorem to see how similar that theorem for the integers is to this theorem now for the polynomials. Now, this is an important theorem, and I'm going to go ahead and sketch part of the proof of this theorem. And again, this proof should ring familiar because it looks in large measure like the proof that we did for Theorem 1.2 that pertains to the integers. Right, so we begin this way. So we're going to let T be the set of all non-zero linear combinations of f and g, where m and n are polynomials in our polynomial ring. And we're now going to let S be the collection of degrees of polynomials that live within this set T. Now, this set S is a collection of whole numbers, and by the well-ordering axiom, we know that S must have a smallest element. And therefore, there's some polynomial, and we can make it a monic polynomial, T in capital T, so that the degree of T is this minimal element of S. Now, this special polynomial T that we've come up with, we claim that this is a greatest common divisor for f and g. To show that T is a greatest common divisor of f and g, we'll have to do two things. First, we'll have to show that T divides evenly into both f and g. That's the topic of the first bullet point. And then we'll have to show that among divisors of f and g, T has the largest degree. That's the topic of the second bullet point. For the first bullet point, we start with the polynomial f, and we're going to divide it by t using the division algorithm. So we get quotient polynomials q and r. We can solve for r in this equation here. And we can write r as f minus tq. Remember, T, however, is a linear combination of f and g, so we'll write T as uf plus vg. And then gathering terms, we see that that's equal to f times 1 minus uq plus g times minus vq. Now, this r had better be the 0 polynomial, as otherwise we have this r written as a linear combination of f and g, and the degree of r by the division algorithm has to be less than the degree of t, and that would violate the minimality of the degree of t. Therefore, because r has to be the 0 polynomial, that means that t divides evenly into f. And if you perform that very same argument with g in place of f, you'll find that t also divides evenly into g. So t is a common divisor of f and g. Now, moving to the second bullet point, we're going to suppose we have a polynomial j in f adjoint x that divides evenly into f and g. Then for some polynomials u, v, m, n in our polynomial ring, we can write t as uf plus vg. Remember, t is a member of capital T, which is a collection of linear combinations of f and g. So t is uf plus vg. But remember, f and g are both divisible by j, so we can replace f by jm and g by jn for some polynomials m and n. And then factoring out the j, we have this. So we've written t as j times some other polynomial. Now, if you look back at theorem 4.2, you would see that the degree of t then must be the degree of j plus the degree of um plus vn. And that means that the degree of j is less than or equal to the degree of t. And that's what we wanted to show, that if we came up with some other divisor of f and g, namely this j, then its degree can't exceed the degree of t. Now, the thing that's missing in this sketch of the proof is the proof of the uniqueness of the GCD, and I encourage you to read that uniqueness portion of the proof in your book. Theorem 4.8 has several important consequences. This theorem 4.10 is one of them. Let's suppose we have polynomials f, g, and h in our polynomial ring over the field capital F. And let's suppose that f divides evenly into the product g times h. And furthermore, let's suppose that f of x and g of x are relatively prime, meaning that the greatest common divisor of f and g is equal to the constant polynomial 1. If those things are in place, then f must divide evenly into h. Now, again, this is a theorem that should look familiar to you because there's a similar theorem that's true for integers. I believe it's theorem 1.4, maybe it's theorem 1.5. At any rate, you should look back at that theorem just to see that it does bear similarity to this current theorem about polynomials. And the proof of this theorem will look a lot like the proof of the theorem that we had back in chapter 1. So we can use theorem 4.8 to write 1 as a linear combination of f and g, namely uf plus vg for some polynomials u and v in our polynomial ring. Now, if we just multiply that equation by h, we get f times hu plus g times h times v is equal to h. But now we know that f divides evenly into g times h. So if we substitute g times h with f times w for some w in our polynomial ring, we wind up with f times h times u plus f times w times v equals h. And then all that's left for us to do is to factor the f out of the left side of that equation, and we get f times something is equal to h, and that tells us that f divides evenly into h within our polynomial ring. Earlier, we were lamenting that finding GCDs of two polynomials seems like a pretty hard task. And you might be wondering, well, if you don't have your computer in front of you, what recourse would we have in terms of finding a greatest common divisor of two polynomials? Well, it turns out that the Euclidean algorithm that we discussed back in chapter 1 for finding greatest common divisors of integers also will work for finding greatest common divisors of polynomials. And it's sort of based on this fact that if you write f as g times q plus r, then the greatest common divisor of f and g is going to be the same as the greatest common divisor of g and r. In fact, that result for integers was something that you proved on an exam, I believe. All right, so the Euclidean algorithm is based on this idea, and it works just the same as it did in the integers. So I have my polynomial x to the fourth minus x cubed minus x plus 1, and another polynomial x cubed minus 1. I want to find their greatest common divisor. The first thing I do is I divide x cubed minus 1 into the other polynomial, and I get a quotient x minus 1 and a remainder of minus x squared plus x. Now, once I've made that computation by long division or otherwise, I just simply slide my divisor down here and my remainder over here and do it all over again. Use the division algorithm to divide minus x squared plus x into x cubed minus 1. I get a quotient minus x minus 1 and a remainder x minus 1. And then I slide over and do this again. Divide x minus 1 into minus x squared plus x. And this time I see that the remainder is 0, meaning x minus 1 divides evenly into minus x squared plus x. And that allows me to conclude that this last non-zero remainder, x minus 1, is my GCD. Now, here we got lucky in that this remainder polynomial is actually monic, right? Meaning the leading coefficient is 1. If you did a calculation like this and you saw the last non-zero remainder, it's possible that the leading coefficient would not be 1. But all you have to do to fix that is to just multiply by the multiplicative inverse of that leading coefficient, and you'll wind up with your GCD. So anyway, the GCD here is x minus 1. Does rely upon doing some polynomial long division, which I have suppressed here. Further, you might remember there's more to the Euclidean algorithm. You can actually back solve in this algorithm to find these special polynomials u and v, so that the GCD x minus 1 is u times the original polynomial, one of the original polynomials, plus v times the other original polynomial. I've not done that calculation here, but you might try it and see if you can compute u and v for yourself.